strategy that's involved in the normal movement of cells from one place to another, enabling the cells that move to start setting up shop in that new site. These are embryonic-like cells in an adult body that provides beautiful opportunities for selective therapeutic intervention. We're extremely excited about this. So let me just sum up by saying the following. In Greek mythology, it was Heracles who crushed Karkinos. Let us think of cancer research as our Heracles, because I strongly believe that it is only cancer research that will turn cancer into the four-letter word that every patient wants to hear: gone. Thank you. It is my great pleasure to introduce my colleague and neighbor with whom we're already collaborating, Dr. Sukak.
Thank you very much, and it is an extreme pleasure to be here with you and to share insights into cancer and the cutting edge of what's happening right now in this field. And I'm Sukak. I'm the director of the NOMA Center for Immunobiology and Microbial Pathogenesis. And I'm an immunologist, so you might be wondering, what's an immunologist doing up here at a cancer panel? And that's because we now have evidence, undeniable evidence, that our immune system can be unleashed to fight cancer. And a particular cell type in our immune system called a T cell is critical to this process, and that's what I study. I'm trying to understand how T cells form, how they function, and how they help us fight infectious disease, and how they can help us fight cancer. A year ago, when I turned 45, it was a very personal time for me, because that was the age at which my mother died of breast cancer. And as painful as it was for me to watch her die, as I'm sure many of you have also experienced with your loved one, it's just a tragic, atrocious process. And as a young teenager, it really affected me. But what I saw in my mother when she was dying was extreme strength and courage, and in ways I've never seen before. And that I saw as gifts that she was giving to me for me to pursue my own dreams and my own passion and scientific research to study and to never give up on these Diana Hargrave.
Thank you, Sue. Yes, my name is Diana Hargreaves, and I am an assistant professor in the Laboratory of Molecular and Cell Biology here under Tony Hunter. And I've been here for just about 2.5 years. And like many of you, I have family members that have been affected by cancer. My father is undergoing treatment for prostate cancer right now. And although I'm very aware of the side effects that accompany these therapies, such as chemotherapy and radiation therapy, it's very difficult to watch a loved one go through this, and also to be aware of the sort of permanent and lasting effects that these therapies and treatments can have. So we're all after that precision medicine that can eradicate the cancer but leave the healthy cells intact. And you heard from Sue about this really revolutionary approach of immunotherapy. We're interested in a complementary approach, which I'll call tweaking the epigenome. So the epigenome refers to this layer of chemical modifications or molecular flags that lay on top of the DNA sequence and tell the cell which genes to turn off and which genes to turn on. This is very important during normal development, and it is the basis for why, for example, your brain cells are different from your muscle cells. But it turns out that in cancer, cancer genes are flagged. In particular, cancer-promoting genes or tumor-promoting genes are flagged. In fact, the cancer cell likes to ramp up the placement of these flags to really produce very high levels of these tumor-promoting genes. And in fact, in many cancers, enzymes that place the molecular flags are actually mutated, leading to widespread. And so this gives us really a window of opportunity for what we like to call drugging the epigenome. And this is the idea that we can develop drugs to block the enzymes that place these molecular flags and thereby reset the genome to its normal level and return the cancer cell to its normal state. And these drugs have already been in development and are starting to enter clinical trials with definitely some efficacy. So our lab is particularly focused on ovarian and gynecological cancers, in particular those cancers that have mutations in these epigenome. There we really know the root of the problem. We're trying to understand how these mutations in the enzymes themselves impact the epigenome and gene expression to promote cancer development and cancer progression. And again, the idea of using these drugs to reset the epigenome and treat ovarian cancer. So with that, I'd like to thank you again for being here tonight, and I'll hand it over to my colleague, Ron Evans.
Thank you, Diana, and welcome everybody. It's an honor to be here to help launch this initiative. I came to Salk 39 years ago, and I'm known for work on genetic switches that control metabolism and metabolism of cancer. Cancer is about facing an enemy from within and often not being able to do anything about it. Frightening, and many feel helpless. It is a very challenging disease to deal with. It's tough to get a diagnosis. My dad was a physician, and in 1974 he got leukemia, brain cancer. The year that I got my PhD at UCLA, my baby sister passed away 3 years ago from kidney cancer. Major loss to our family. But what set me on my course of her cancer research, working to the loss of my brother at the age of 30, my older brother at the age of 30, myeloid leukemia. At the time had no drugs, no therapies, but nothing that we could do for him. I tried to figure out at that age new therapies, various books, but there was no therapy. We lost him. Yet 14 years later, my lab discovered the secret to that disease. And from that, we were able to identify a drug called retinoic acid, a form of vitamin A, that now is able to cure 90% of the people that get that disease. So although my brother was not able to benefit from it, this was a major advance, and in honor of him is what really drove that process. So people make a difference, your loved ones make
person and a huge impact on the field. This was before he won the Nobel Prize, but he was just such a major figure. And at Salk, our daily job is to come and try to tackle the most difficult problems. I'm now working on pancreatic cancer. I'm going to show you a little bit of that in this picture where the cancer is being surrounded by this barrier. And it's generally considered untreatable. And actually, this is not the real image of the cancer or the barrier around it, but rather this is the actual barrier reef, a picture that I took from a plane. But it illustrates the idea. But why does this happen? It really literally gets a shield. Like in Harry Potter, there's the invisibility shield, and the drugs and the immune cells cannot get to it. They can't find it. Our goal is to take down that shield and break up the barrier. So in the end, we believe that knowledge is power. Knowledge really is power. And the way in which we attack this is by identifying a weak spot using genomic sequencing to find that the vitamin D receptor was the key secret to taking apart this barrier. Vitamin D, the sunshine hormone, can unblock that field and unleash the power of the immune system to come in and take out the tumor. And I'm going to just show you a little illustration of that in this little animation where the tumor is locked inside. The vitamin D form that we have comes in, decodes the barrier, and exposes the tumor so that the immune cells can now come in. You can see now they're beginning to take out the tumor. This is actually a major conceptual advance, but because it's striking, it has a lot of clinical implications. And so while being a basic scientist, by partnering with our clinical collaborators, not just at UCSD, which we do, but at Memorial Sloan Kettering, at Harvard, at UPenn, in Cambridge, England, we have partners everywhere. Why? Because if you discover something, people want to get it into the clinic. So we have multiple clinical trials that are ongoing. And with this, we think that this kind of therapy makes something possible that was once thought to be impossible. So I believe there is a treatment and possibly a cure for every cancer. In the end, finally, I just want to say that not only thanks to everybody here, but everyone here can make a difference. Each one of you can help. While Jonas Salk said that hope lies in dreams, you saw that when Ruben had his slides, we in the Cancer Center know that science can turn those dreams into reality. So that by believing in Salk, you believe in the future and possibly in a world without cancer. Thank you.
Okay, very good. One of the questions that a number of our guests asked when they sent in their questions was, is a cure possible in our lifetime? Jeff, you want to start us off on that one?
Sure, thanks, Marna. So this is a common question that's asked. Is there going to be one cure for cancer? You know, if cancer was one disease, I believe we would have found it already. But I think as we've hinted at already, cancer is an umbrella term that describes numerous diseases. And as you've already heard, for some cancers that were thought of as death sentences even 15 years ago, such as the one that Dan Lewis had, there are now treatments to successfully counteract that cancer. Dan is living proof of that, as are many others. Now, there will be cancers that are so complicated that one drug won't be sufficient. And so combinations of therapies will be needed. But even then, probably for a number of cancers, they won't be cured. They may be controlled. Now, I think that a person who could live with instead of die from their cancer would be happy with such control. But I think we've only touched the tip of the iceberg. We're we're only starting to mine the depths of the knowledge that we're gaining. Use that to fuel the development of other approaches, such as I think Jim might want to talk about.
So as I mentioned, immunotherapy is revolutionizing cancer care, and probably every treatment going forward will involve immunotherapy with another combination. And we are seeing cures today. There are a fraction of patients they have metastatic cancer, they're going to die in a few months, they get immunotherapy treatment, and their tumors melt away. Metastatic disease evaporates, and they've been living now for many years. But the reality is that this is a fraction of patients, and so what we have to figure out is how can we make the numbers of patients benefit, how can we combine these treatments, understand the new, incorporate many different processes that are occurring within the tumor to cause the tumor to grow, to evade the immune system, to change the other cell types that are in that environment that are allowing that tumor to progress, because they're all feeding that tumor growth. So we need to intervene in multiple different ways, and that's the only